In this video, I'm going to introduce the simplex method. The simplex method is another method for solving linear programming problems. We've already looked at the graphical method for solving linear programming problems, and so the simplex method is a little bit more algebraic. There are three different types of problems we're going to be looking at: standard maximization problems, standard minimization problems, and then non-standard max and min problems. Today we're just going to look at standard maximization problems. So the first thing we need to be able to do is to recognize when a linear programming problem is a standard maximization problem. So a standard maximization problem is an LP problem in which we are required to maximize, as opposed to minimizing, an objective function. So we've already discussed what the objective function is. And when we're maximizing, we usually let this variable over here on the left-hand side be P. And again, I like to think of it as P for profit, something that we would maximize. So this would be the objective function. It is linear, some constant times an x plus some constant times an x sub 2 plus a constant, and there could be many different variables. X sub 1, x sub 2, x sub 3, x sub 4, on and on and on. Or we could just call them x, y, z. Subject to constraints. So we have the non-negativity constraints, that's what these are, and then we have our linear constraints. B sub 1, x sub 1, b sub 2, x sub 2, plus ... b sub n, x sub n. The key is right here. The inequalities have to be less than or equal to, and this C value on the right-hand side must be positive, right? So C is non-negative, which means it could be 0. Non-negative means that C could be positive or 0. And it is important that the inequality be a less than or equal to sign, not equal, not greater than or equal to. So let's just take a look at a few examples. Maximize P equals 2x minus 3y plus 3z, so that looks good. And here are the constraints. So what we're looking for with the constraints are the less than or equal to sign, and then this number being positive, which they are. In the second constraint, less than or equal to, and a positive 6. And then these are our non-negativity constraints. So this is a standard maximization problem. Example 2, again, maximize P equals 2x sub 1 plus x sub 2 minus x sub 3 plus x sub 4. That looks good. Subject to the constraints, we have a less than or equal to 0. That is non-negative. Less than or equal to 1. That is non-negative. Less than or equal to 2, non-negative. So these are all less than or equal to's, and these are all non-negative. And then we have our non-negativity constraints, saying that all of the variables x1, x2, x3, x4 must be greater than or equal to 0. The third one, this is not a standard maximization problem. The objective function is okay. Maximize P equals 2x minus 3y plus 3z. But here we get into a little bit of problem with the first inequality. We have a greater than or equal to 7. So that makes it not a standard maximization problem. The second inequality is okay, less than or equal to, and a positive 6. Now what this is telling us down here is, as we know, we could take this linear equality, we could multiply both sides by a -1, and that would change the direction of the inequality. We would end up with a negative 2x minus z is less than or equal to -7. That's written down here. But the problem now is this -7. Remember, this value has to be positive. So this is not a standard maximization problem. So I'm going to do example 1 from my notes. I've written out everything, and this is normally what I would be going over in class, but I'm going to go over it in the video, and then I will do a couple of examples in other videos. Step number 1 is convert to a system of equations by introducing slack variables to turn the constraints into equations and by rewriting the objective function in standard form. So what we do is we start with the first constraint. and we rewrite it here, but we're going to write it as an equation. So we're changing it from an inequality to an equation. So if 2x plus 2y plus z is either less than or equal to 10, and we're going to change it to just being equal to 10, well, what if the original inequality, it was less than 10? If 2x plus 2y plus z was actually less than 10, and we're changing it to an equal, it would not be equal, because this quantity over here would be less than 10. So what we have to do is we add the slack variable. And the slack variable could take up the slack. It's whatever we would need to make the left-hand side equal to 10. And we don't know what that is. So we just put in a variable and we'll call it s. S is called the slack variable for the first inequality. And then we do the same thing for the second inequality. X plus 2y plus 3 is less than or equal to 15. And we're going to change that to equal 15. So we have to introduce another slack variable. We use a different slack variable for each constraint. So I'm going to use t for this one. And then finally, we take the objective function, and essentially what we're doing is we're taking everything on the right-hand side of the objective function and subtracting it to the left-hand side. So 3x subtracted to the left-hand side would be a minus 3x, and that's what we get down here. 2x subtracted to the left-hand side would be a minus 2y. Positive z subtracted over to the left-hand side would be a minus z plus the p, and now the only thing left on the right-hand side over here is 0. So that's the first step. Make sure that you understand that. Look at the various examples, and I will be doing another video with a couple more examples of how to do that. So step one is to create the system of equations with the slack variables. Step two is to write down the initial tableau. I like to just call it a table. And so this is kind of like what we were doing in the last section. You're going to see that there are some similarities to when we were creating matrices in the last unit. So we start by creating a matrix-like table, and the table will have an x column, and that will have the coefficients of the x variables in it. So 2, 1, negative 3, 2, 1, negative 3. Then we have a y column, and so that will have the coefficients of the y variables, 2, 2, and negative 2, 2, 2, negative 2. Then the z's, 1, 3, and 1, or negative 1. Now, we have our slack variables. We have a 1s here, 0s is here, 0s is here, so we have a 1, 0, 0. The next slack variable is t. We don't have any t's in the first equation. We have 1 t here and 0 t's here, so we have 0, 1, 0. Finally, the p. We have 0 p's, 0 p's, 1 p, so 0, 0, 1. And just like with our augmented matrices in linear algebra, we have a constant column, which is always the column on the right, 10, 15, 0. 10, 15, 0. It's important to make sure that you always write the objective function on the bottom, so the objective function will be the very, very, very bottom row. So this is what is called the initial table. Make sure that you label the column headings properly. And then one last thing is this explanation of active variables and inactive variables. This is called the initial table. The slack variables and p will be what we call the active variables. So s is an active variable, t is an active variable, p is an active variable. We then write the active variables as our row headings. This would be the s row, active variable s, s, active variable t, t, active variable p, p. So it's very important that you write these over here also. All right, now this is being the initial table. And I'm going to explain how to find the values of all of our variables, x, y, z, s, t, and p, from the initial table, because this is the same procedure that you will use every time we create a new table. So we start with the value of our first active variable, s. Okay. How do we find the value of s? Well, we always go way over to the constant column. So we take 10. And now we look for the S column. Here's the S column, and here's the S row, S and S. So we have a 1 right here in the S column and the S row. So we take the constant 10 and divide it by 1. 10 divided by 1 is 10, so S is equal to 10. T is our next active variable over here. We're going to do the same thing. We take the constant, 15, and then we look for the T column and the T row. Here's the T column. In the T row, we have a 1 here. These won't always be 1s. They're 1s now, but they won't always be 1s. So 15 divided by 1 is 15. So T is equal to 15. P, we do the same thing. We take the constant, which is just 0, divided by the number in the P column and the P row, which is 1. 0 divided by 1 is 0. So P is equal to 0. So we found the value of our active variables, S, T, and P. Finding the values of the inactive variable is easy. They're always 0. The inactive variables, X, Y, and Z, are all equal to 0. And so this is sometimes referred to as the basic solution, which is always associated with the initial table. The next step is using the table is to select the pivot column, right? The pivot column. And to do that, we're going to choose the negative number with the largest magnitude in the left-hand side of the bottom row. So here's the bottom row. By the left-hand side, I mean everything except for the constant column. So if we look at all of these numbers right here, we want the negative number with the largest magnitude, or in other words, the most negative number. Well, that's going to be negative 3. Negative 3 is the most negative number in the bottom row. If there are 2 or more candidates, choose either one. In other words, if there were 2 negative 3s, if this was a negative 3 and this was a negative 3, choose either column. So this is our pivot column, and so that's what we're showing right here. This is the pivot column. The next thing is to find the pivot in the pivot column. So select the pivot in the pivot column. The pivot must always be a positive number. So negative 3 cannot be the pivot. 2 is positive, 1 is positive. So either one of those could be the pivot. For each positive entry B, so these are our B values, in the pivot column, compute the ratio of A divided by B, where A is the number in the last column. So this would be the A value. So if I just put a little A up here, and this would be my B value. So we're going to take the ratio of the number 10 divided by 2. And I show that down here. We take the 10, divide it by 2. 10 divided by 2 is 5. We do it for the second column. Take the constant, 15, divide it by 1. 15 divided by 1 is 15. We want the smallest ratio. So the smallest ratio, the smallest number is 5. So that means, because the smallest ratio is in the first row, that means the number in the pivot column that's also in the first row is going to be our pivot, and that would be the 2. And I like to highlight the pivot. Somehow, just denote what your pivot is going to be. So 2 is the pivot. It's in the pivot column, and it is in the row that has the smallest ratio. Okay. Now we get to a little bit more like the linear algebra that we've learned in the last unit, because the next step is to use the pivot to clear the column in the normal manner. In other words, we're going to use Gauss-Jordan elimination now to clear the column. So you remember what we did in linear algebra. we would normally take the pivot and turn it into a 1. We're not going to do that now. The second step in linear algebra was once we turned the pivot into a 1 was to get the zeros below it. That is what we're going to be doing now. And so we want to change this 1 into a 0. And so we're going to use a row operation to do that. And then we're going to apply that row operation to the entire row. So the row operation that we're going to do, I've written down here, is 2 times row 2 minus row 1. And we always want to write these in this form over here. The row to change plus or minus the pivot row. The pivot row would be the first row, the one that has the pivot in it. So the row that we're changing, in this case, is row 2. We want to change the 1 into a 0. So we're going to take 2 times row 2. So if I take 2 times 1, I get 2, minus row 1, which is a 2. So 2 times 1 is 2, minus 2 is 0. And we get a 0 here. And then we apply that to the entire row. Now, to change a -3 into a 0 using the pivot, we're going to use multiples. We know that 2 times 3 is 6. So if I take 2 times the -3, I get a -6. Plus 3 times 2 would be 6, and a -6 plus 6 would be 0. So here's the row operation. 2 times row 3 plus 3 times row 1 would give me a 0. And then you apply that to the entire row, and you've got your next table or tableau. Now, in this particular problem, we are done already. As it says up here, if all the numbers in the left-hand side of the bottom row are 0 or positive, we are finished. And so that's what we have now. All the numbers in the bottom row are positive or 0. So we are done in one step. Sometimes you can take 2, 3, or 4 steps. So now how do we figure out what the solution is? Well, this is where we have to figure out the values of the active variables. But one last thing is we have to change an active variable. Notice it says change from S to X. So here's what we do. This was our pivot. Okay? It was in the S row and the X column. So what we're going to do is we're going to replace the S with the X. And so that's why the S became an X. That means that X is now a new active variable, sometimes referred to as the entering variable, whereas the S was the departing or exiting active variable. So X, T, and P are our active variables. And so the way that we determine the value of the active variables is, just like we did with the initial table, we go to the constant column, take the 10, and divide it by the number in the X row and X column, which would be 2. So 10 divided by 2 is 5. So X is equal to 5. T is an active variable. We take the constant 20. We look for the T column. The number in the T row and the T column is 2. 20 divided by 2 is 10. So T is equal to 10. P is an active variable. 30 divided by the 2, because it's in the P column and the P row, 30 divided by 2 is 15. So P is equal to 15. Then all of the inactive variables, which would be Y, Z, and S, are all 0. Remember, the inactive variables are always 0. So these all just become 0. So X is 5, T is 10, P is 15. Now remember what P is. P is our answer. The optimal solution is 15. Now that optimal solution occurs when X is equal to 5, Y is equal to 0, and Z is equal to 0. And that is a linear programming problem using the simplex method. So I know there's a lot of terminology, there's a lot of new procedures. This takes practice. So I'm going to post another video where I go through and do example number 2, and then I'll do another video with example number 3. So I hope this is helpful. Let me know if you have any questions.